Hey everyone, we are going to be looking at the derivatives of inverse trig functions. So first of all, a little bit of background. Just a reminder about inverses. So think back to pre-calc or maybe algebra 2 where you switched x and y and then you solve for y. Sometimes you have to do like some domain limitations. Or graphically, if you just reflect a function across the line y equals x. So for example, root x and x squared are inverses of each other with that limitation on the domain for x squared. This hopefully is sounding vaguely familiar, I hope. So we're looking at inverse trig functions, which you might think of as like backwards trig. Remember like doing problems like what if sine of the angle is 0.5, what was the angle? And you can do that inverse trig, so that backwards trig thing on your calculator. Sound familiar? So that's what we're looking at. And so a little bit of a notation warning. The way it gets written, and this is, you see it on your calculator. If you look at your calculator right above the sign button, you see a little sign with a -1 exponent looking thing. These are not exponents. I'll say it again. These are not exponents. This does not mean like 1 over sine x. We actually have something for 1 over sine x. It's called cosecant x. So when you see this -1 on any of these, it does not mean 1 over. It's not the reciprocal. It is the inverse. And it's just, and like same with the function notation for inverses with that f -1 thing. Remember that? It's a truly unfortunate bit of notation because it causes a great deal of confusion. But you just have, so that's something you have to automatically know. Okay, normally I would give you where all of these come from. Sometimes I don't. Today is one of those days. I am not going to give you the whole background. If you want to see the graphs of these 6 functions, take a look at page 149 because there are some really nice graphs in our textbook for it. If you want a little more reminder about inverse functions, check out pages 146 and 147. And if you are really keen, feel free to take a look at the proofs for the derivative of tan inverse x and secant inverse x. I'm not going there. So these are pretty overwhelming looking, but there's some good news. Remember how when we did the derivative of the other trig functions, I had said all the cos have negative derivatives? The same is true. In fact, in this case, the co-derivatives are exactly the same as their buddies, but just negative. Like they're totally the same. But they are these kind of awkward, annoying sorts of things. And we have to be really careful when we're using them. So, and also while you're using all these, all the other previous rules that we have, you know, chain rule, product rule, whatever rules, they fall into play too. So, gosh, there's a lot to keep track of. So we're going to add these guys to the list. I know you want to do that. Just hit pause, write them all down, you know, like a good student does. Okay, let's take a look at an example of using one of these. So say we have y equals cotangent inverse of x plus 4. So the derivative to this is, the derivative of cotangent is negative because it's a co, and it's 1 over, and then 1 plus whatever it is inside squared. So that x plus 4 squared, quantity squared. And then times derivative of the inside because of the chain rule. But the derivative of the inside is 1, so that's not very interesting. Okay, I'm going to go rogue. I'm going to change this problem. We're going to make it 2x plus 4, just so I can show the derivative of the inside. So we have 2x plus 4 there. And then times derivative of the inside, the derivative of our inside is 2. And that's it. We don't need to clean it up. I'm not interested. So let's do another quick one. So say we have y equals secant inverse of, oh, I'm just going to go mean on this. Oh, tangent x squared. This is cruel, I'll admit it. So y prime is 1 over, so for secant, it's you have your, like whatever's in that x spot is just whatever your inside is. So I have absolute value of tangent x squared. And then I have a radical, and then I have my inside which is tangent x squared, getting squared minus 1. All of that's under a radical. And then times the derivative of the inside. So the derivative of tangent is secant squared. So derivative of tangent being secant squared. Keep its inside the same with that x squared. And then times the derivative of our inside, 2x. This is a spicy problem. If you can do this, you're really good at this stuff. So it's pretty gross, but it can be done. Just pay attention to the chain rule. So here is just a quick example, couple examples and our equations for this. By the way, my little memory trick on this. So I always think that secant and cosecant, I mean, they're such rare functions anyway, let alone the inverses of them. These are the weird ones with this absolute value x. And when I look at inside the radicals on the derivative of sine inverse and secant inverse, I'm always like, ooh, which is it? 1 minus x squared or x squared minus 1? So the story I tell myself, knowing that x squared's a positive thing, absolute value x is a positive thing, these positives, you know, they're BFFs. They like to stay together and be positive together. So the x squared and the root and the absolute value x, they just stay really close. So that's my really bad story with no plot about the order on this x squared minus 1 versus on the derivative of sine inverse being the 1 minus x squared in there. It's a terrible story, but if you struggle to remember things like I do, you make stories up. So there are our derivatives of our 6 inverse trig functions and a couple examples using them.